Hey guys, and welcome back to the YouTube video. In today's video, I'm going to be teaching you how to create a neural network that can guess whether a hand has made either a rock, a paper, or a scissor. We're going to be using the TensorFlow module of Python, and the dataset that we are going to be using is called the rock, paper, scissor dataset. It's a part of the TFDS, also known as the TensorFlow datasets. So loading in will surely be a bit difficult than the Keras datasets, but it's going to be a bit easier. So let me get started. As I told you, I'm going to be working with a Google Collaboratory, and so I'm going to go ahead and import the modules first. I'm going to be importing the model TensorFlow SDF, and from the TensorFlow module, we are going to be importing Keras, and we are going to be importing TensorFlow underscore datasets. So TensorFlow datasets are a bunch of datasets that TensorFlow has to provide us, and it's also pretty good. So that's why as TFDS, because TensorFlow datasets is a pretty large name, and we do want to refer that every time when we are um, doing something with the TensorFlow datasets. And we are going to be also using the NumPy module of Python. So import NumPy as NP, and we will also use matplotlib. Alright, so we have made all of the imports, and one last thing that I'm going to be doing over here is I will type out tfds dot disable underscore progress underscore bar. The reason why I'm doing this is because when we will load in the data, it will show a bar that will show how much of the data is downloaded and all of that, which I don't think is that necessary to see. So if we just put this command in there, then it will not show us that. So now let me actually show you what the dataset looks like. So we can access it pretty easily. All we do is just make a variable called builder is equals to tfds dot builder, and now we just simply need to put in the name of the dataset, so rock, paper, scissors, and then all we do is just type out info, a variable is equals to builder.info, and then we can just simply print out info to the screen, and you will see it will show us the info. So it will take a second or two to run, but then it will throw us the output that we need. Alright, so you can see it says TFDS code dataset info, the name is rock paper scissors, and this is the version. So let's have a look that the versions correspond. And the description is pretty simple. Images of ants playing rock paper scissors game. Everybody knows that game. You can see the image shape is 300 by 300 by 3. We don't need to, and it's U int 8. And there are 3 classes which are going to be rock, paper, and scissors. So yeah, and there are 372 test images and 2520 train images, which I feel like it's pretty good. We got the author over here, got the title, and the alright, so I'm not gonna print it out every time. So now let's actually make another block of code, and over here I will just type out ds underscore train. So we are obviously going to be using the training data and the testing data, and now we will load in the data. To do that, it's pretty simple. In TensorFlow, it's kind of like Keras, but a bit different. So tfds dot it was, I guess, load. Yeah, it was load, and then we need to put in the name of the dataset that we are going to be using. So it's rock paper scissors in our case. So what we do is just copy that and we just simply paste it down. And now what we need to do is we need to define a split in here. So we need to split it into the training data, because as we all know, there are 2 types of data in machine learning and neural networking, all the training data and the testing data. So that's why. So now I will make another variable called ds underscore test is equals to tfds dot load Now I want to load in the same thing again, but this time the split that we are going to be using is going to be a test split because we can see it's the test one. So now we can simply just run this block of code and it should download and prepare the dataset for you. Now if you would have not written this command called disable progress bar, it will show a little bar where it will download the dataset, but it's quite annoying, so I've got rid of it. But you can try and commenting out this code and see what you get. So I'm going to make another code block, and now we will actually see the examples on how these hands look like. To do that, we just type out a variable called fig, and then we just type out tfds dot show underscore examples. So show examples, and we want to show the examples that are that of the info because that's the dataset that we are using, the rock paper scissors. And now we can just type out what example we want. So I can just type out ds underscore train, and then when I just run the code, it should make these images, as you can see. Now the images that are over here are like automatically generated, so they are not exactly hands. They were stimulated in the computer, so you will see some of them are a bit weird. As you can see, this paper guy is a bit sketchy. Looks like some sort of a vamp. So yeah, so we can also go ahead and show the testing data. So a lot of people think that if we show the testing data, the model will actually get tested and all of that. No, it's not like that. Even if we show the testing data right now, nothing is bad for now. So actually, let me go and put in training data. So if you guys don't know anything about neural networking, still follow along. You'll know a lot of things by the end. So now what we will do is we will take our training data and convert it to a numpy array, and or also what we will do is we will kind of shorten the data. So we will type our train underscore images is equals to a numpy array, and the numpy array will be containing the example, and it will be an example image and dot numpy because we want to convert the things that are ahead of this to an numpy array. So colon comma 0. So basically what this means is we convert the RGB to a single color scale. So that is pretty good. Now you might be thinking that when we are using something for a neural network, we example for this we need the color scales, but it does not really matter because in the rock paper scissors example, as you can see, if we run the training data, then the things that we want to grasp is by the edges of the fingers and the fingers that are projected outside. For that, we could use some convolutions in the neural network by using a CNN or a convolutionary neural network, but we will not use that for this tutorial. So for now, we just make a simple little for loop. So for example in dataset train, so this two lines are going to be a little bit complicated, but it's okay. Now we will just take this code and we will paste it down here, and instead of train images, it has to be train labels, and image will become label, and I don't think we need to change anything else. Now I'll just copy this and I will paste both of these over here, and instead of train images, it will now become test images because we also need to clean up the test images. So I will just turn this to test images, and we also need to make this ds underscore test and ds underscore test. So this was pretty simple, and we also don't need this over here because we cannot convert a label into a gray, like we cannot remove the RGB from a label, so that's why that's pretty obvious. So now what we will do is we can specify the class names. So this is not super like important, but still. So it's going to be rock paper and scissors, because these are the possible predictions a model can make. So now we can finally make the model. So I'm going to go model is equals to keras dot sequential, put the parentheses and the square brackets. I don't know why this indents me over here. So I'm going to be first adding a flatten layer on top just to flatten the data that we have. And now I'm going to be adding a dense layer. So layers.dense. This will be have something like 560 nodes, and we are going to be going with an activation function, which is going to be a rectify linear unit, also known as a ReLU. We are going to be going with another dense layer, so keras dot layers dot dense. So this I will probably make a bit smaller, like 250 nodes. And again, we are going to be going as an activation of a rectifier linear unit. Now what we need to do is now I'm going to be making the output layer. So keras dot layers dot dense. Now this will only have 3 nodes or neurons. The reason is that the possible predictions we can make are only 3, so that's why the output layer should have a total of 3 neurons or nodes. And the activation is going to be softmax, as it works really nicely for a output layer. You could go with some different activation like sigmoid, which I always encourage people to try it out. But I'm going to be going with softmax because it was already tested. This model is already made over here. So yeah. So now what we will do is we'll make it so that we can actually compile the model. So I'll just type out model dot compile, and we are going to be using an optimizer of the Adam optimizer, and the loss function that we're going to be using is going to be called sparse categorical cross entropy. And the metrics we are going to be using are the accuracy metrics, and I feel like we can now finally fit the model. So model of fit, um, it's going to be train underscore images, comma train underscore labels, comma the epochs are going to be 5 epochs, and the batch size will be 500. So I feel like we can let me just run the code. The model is finally ready. Let me have a look over here. It's ready in pretty quick. You can see just 13 minutes. So that's pretty good. We made an ML model in like just 13 minutes. So now what I'm going to be doing is change the runtime type to an hardware accelerator of a GPU. So it kind of runs quickly. So now we will need to please run all of these cells, or else the code won't work. So it's, it will take some time, some seconds, but the epochs will just run so quickly. Try doing it without a GPU hardware accelerator, and try doing it with a GPU hardware accelerator. You will see a very big and a massive difference in the speed of your neural network. So that's why a lot of data scientists use a GPU on their PC or laptops. Now that's why I really like Google Collaboratories, because we can use something like a GPU for around it. And you can see the accuracy is kind of, I would say, yeah, I don't get it why the accuracy is like so bad. The reason is the batch size is 500, which is so big. We are going to be going with only a 32 batch size, and you can see uh, the accuracy has actually boosted. And so, and I can also just go ahead and we can also write the loss function as something like that. Keras dot losses dot sparse categorical cross entropy. So that's also a way in which you can write your loss function. Obviously, it won't really change the accuracy, but I just thought I would show that to you guys. Just something. So what I will do now is let me. So now we have actually created the model. Like the model is ready. We could go ahead and look at the prediction that the model makes. Like using model predict, but I'm not actually going to be doing it. But you guys can just type out something like prediction is equals to model dot predict. I need to open up my code for this. I just need to check something. Before that, let's actually use this and actually show it. So I will just type out plt dot show, and we just type out plt dot im show, and we want the train images of index 0, and we can go cmap as grays underscore r. So it's going to be a grayscale image. I just need to check this thing. So now what you can do is you can just go. Now this will actually throw us an error. The reason being the shape of our data is quite, I would say, absurd. It's 300 by 300 by 1, because the way we are did all of this will require some extra processing, because the data was actually a tensor and then we converted it to a numpy array. So that actually would make the model a bit better, but it would require a bit more processing. So to do that, what we can do is simply just type out image is equal to train underscore images 0, and we just type out dot reshape as 300 by 300. So we remove that 1 which was once present over there. So now if I just run the code, you will see it prints out. You don't need to care about that, but you can see it prints out that kind of scissor kind of thing. And the cool thing is I can even go ahead and test image, and you can see it made that kind of finger, the finger. So you could go and make a convolution layer out of this. Like you could add a conv2 layer and a max pooling layer, but it actually reduced the accuracy of my model, because the convolution that I had added actually did not detect anything that was that major. Like even after adding 2 convolutions, the network just was pretty bad, and sometimes the convolutions are not the best choice, and you would need to add like tens of convolutions to get yourself a pretty successful layer. And you could actually like get a pretty good layer with just 3 dense layers, and why add a convolution to that. What you guys can also do, I'm not going to be emphasizing on that much, because it's just for the user to like get to know a bit more. So just go model.predict. I need to have a look over here in my VS Code for a second, because I was a bit finicky on this one. So just a second. Alright, let me have a look. I've already made it, so I know where it is. Neural network, ML, machine learning, not that. It has to be somewhere. But I feel like it's not here. But let me actually have a look. I might be having something related to that. Just let me try and show it to you. What we are gonna try and do now is we can to show it actually in the matplot.net form, so you guys can get some kind of visualization. I don't know if I'll be able to do it right now in this tutorial, but whatever. You guys can try it out. So what I need to do is type out prediction is equal to mod.predict the test images, and then all you need to do is actually I need to implement it right here, and we also need this to go over here, and then what we can do is let me actually show it to you guys. So all I can do is just go for I in range for like 5, and then what I can do is I can just go and indent all of this over there. Then what I can do is I can just go over here and just type out plt dot grid as false, plt dot title, make the title as prediction, we just need to do that, and plus the class names, and then we just use a numpy function called np.argmax. We want to argmax the prediction, so the prediction of the ith index, which is going to be the for in range. And now you want to see the actual thing, so pld.x label actual, and we can just type out test underscore labels items. So that's how it is done. Let me have a quick look. I feel like it won't work, but I am trying it out. So it must be a string, not a numpy int. Alright, I get it. So the test labels, what was the test labels? So the test labels that we were using here have been converted to a numpy array. So I feel like instead of converting it to a numpy, we need to convert it to a string. I don't know if this will work. I'm not sure, but I am trying it. I don't know if it will work. I'm not at all sure. I've never even done that. For example, that's not supposed to be there. Don't know why. Let me try it again. Even after using a GPU or an accelerator, it's doing fairly slowly. Don't know why. Right, eager tensor object has no attributes. Alright, I got it. So this is like a tensor. So I can't actually convert it to a string. So that's a bit of a problem there, over there. What if I just get rid of that? I feel like it should work. So the prediction is scissors, the prediction is rock. That's wrong. Scissors is right. I don't know why it's getting wrong on that. Oh, I get it. What the thing that's happening is I need to bring down the stupid. So yeah, now it's okay. So the prediction is rock, prediction is scissors, prediction is a rock. That's a paper. I don't know why it predicted it as a rock. It's obviously up to the network. It's not up to us. But so this is the entire neural network. What I'm gonna say, it's surely not the most advanced thing you would have ever seen in the world. Like, you might have seen some more crazy complex neural networks before, but I just feel like if you are just a beginner in machine learning and I've just used the Keras datasets, then you will really like this neural network, and also because it's associated with like a pretty old and a pretty cool game. So if you like rock paper scissors, then you're obviously gonna like this neural network. So what I encourage you guys do is you add some more dense layers and increase the accuracy of the model that we have created over here, because that's quite important. The accuracy that we have now is working fairly well. You can see it's like scissors, rock. Sometimes obviously it's doing some wrong thing. If we just increase it to 15, that's the way it is. Prediction paper. Wow. So this is pretty good, because it's like really simple to do, and it's also very easy, I would say. Don't know why it's not predicting anything as a paper. Alright, so I don't know why it predicted the rock as a paper. So if you guys find if there are any mistakes in the network that I created, you guys can totally let me know in the comment section down below. That day I made some sort of little oopsie. I will surely try to fix that. Like, but I myself am not that great at neural networking right now. I've just started out. I'm learning some more new things, so don't expect me to be really like a pro in neural networking. So you can see it's predicting some things as wrong, which I don't get it. Like, I don't get it why it's predicting it as a wrong. It should not. The thing is, it's predicting all of the scissors pretty nicely, but the paper and the rock are not the best. I literally sometimes feel like there's a mistake in my model, and I don't think. I also change this. Scissors, scissors. The cool thing with this model is that the model is like even if we don't have an actual label, we can easily get it at what it is. The reason being, this is like we can see what this can. We know what it is. It's a scissor. This is also scissor. This is not a rock. That's a complete paper. Look, it's like it's going like scissor, scissor, rock, scissor. I don't know why it's going rock over here. Like, I don't get it. That's surely not a rock in any ways. So what you can also do is just go and just type out model dot evaluate, and I think we need to pass it test images, but I might be wrong. I don't know. So what it does, it evaluates the boy, that's bad. Oh my god. The model that we created is pretty good on training images and some testing images. But on the evaluation, you can just have a look at what it's doing. So yeah, that's all. That's pretty bad. But at least the model works fine for like the training part. So you can just have a look. It's not evaluating properly, but it's alright. We can work with it pretty nicely. So this is the entire model. If you like the video, that's pretty. Thank you. If you so the model I created over here is pretty better. So that's it for this video. If you did like the video, comment down below. Tell me what next neural networking kind of things you want to see. I will surely consider it and try making some more difficult neural networking. I'm thinking of making some different neural network, but we'll see. So that's it for today, guys. I hope you enjoyed the video. If you did, like and subscribe to the channel, and until the next time we meet, bye bye.